Now that we've learned a variety of techniques of integration, we're going to start to look at some applications of integrals. And the first section has to do with thinking about definite integrals in terms of measurement. So the first topic we're going to cover is finding the area between two curves. We know that an integral is the area under a curve, meaning the area between the function and the x-axis. However, there are cases where we want to look at different areas, such as the area created by these two overlapping functions, which you see shaded in the first picture. So in this middle graph here, we know what the integral of f of x dx means. And specifically, I'd like to go from this intersection point, which is actually located at 1.5, if you pay attention to the scale, all the way to this intersection point, which is at 4.5. That integral is just the area under that particular function, and function f of x is right here. So it's this blue area. Now in the next picture, I'm going to look at what the meaning of the integral of g of x with the same limits would be equal to. So I'm going to go to my two intersection points, and I'm going to shade the area underneath this curve to the x-axis. Now g of x is this upward facing parabola, so the region that we're talking about then is this purple one. So now looking at all three pictures together, if I want just this shaded area, the blue integral is calculating too much. It includes that shaded area, but also includes this stuff down here. Well, that stuff happens to be represented by the second integral. So if I were just to subtract that off, I would in fact have the proper area. So what we're going to find is you can always find the area between two curves by taking and integrating whatever the top boundary function is minus whatever function is forming the bottom boundary. So this gives us the basis for finding area between two curves. Sometimes we do integrate in terms of x, which is the situation above is a perfect example. And so when we write our integral, again, we always want to have the topmost function first and subtract whatever function creates the bottom boundary. However, there are times where it's appropriate to think about integrating in terms of y instead of x. In that case, instead of thinking of top function and bottom function, we're going to think of the rightmost function and the leftmost function, and we'll integrate in terms of y. We'll look at examples of both of these. The first example, again, not in your book, is to find the area of the region bounded by these two functions, f of x equals 2 minus x squared and g of x equals x. You will always want to begin by graphing your functions. If you do have graphing software to use, you can do that, or you can always just fall back on making tables of values for the things you're looking to graph and graph them that way. So I'm going to pick some x values, some negative, some positive, to substitute into each equation to find the corresponding y values. So by substituting my x values, I generated the y values for each equation, and I also went over and graphed those equations. Now, the shaded area that represents the area between the curves would be this little portion right here. So now I can write an integral that will allow me to find that particular shaded area. And to do that, I'm going to remember that we integrate the top function minus the bottom function. We integrate in terms of x when we're doing top minus bottom. And my limits of integration come from the intersection points. So here we have a leftmost intersection point of x equals -2. And I'm going to integrate to the rightmost endpoint of the shaded area, which is at x equals 1. So my limits will be -2 to 1. Now I go ahead and write each function in the correct spot. So my topmost function is this curved boundary, which is being created by the function f of x. So in this case, f of x should go first, minus, and the bottom boundary of my shaded region is represented by g of x. I substitute those functions into this integral, so I would have 2 minus x squared minus g of x, which is just x, dx. And all that's left to do is evaluate this integral. So you can see I have found the antiderivative. Then I'm using fundamental theorem of calculus to substitute values. And when you compute all of this math, you end up getting a value of 4.5. Now, are there some wrinkles that can occur with this? Absolutely. And that's what's coming up next. When you're finding the area between two curves, it's possible the functions cross over each other. Which one is the upper boundary and the lower boundary might switch. And in this case, you're going to write separate integrals for each region and combine them together. In the next example, you can see the graph has already been created for us. And we're looking for the area of the region between the cubic and the quadratic. Now the cubic is the one that's kind of bouncing, going up and down. So this is my f of x. And the one that's curved downwards, the parabola, is my g of x. So you can see if we wanted to find the region between the curves, I have an intersection point here. I have this purple area between the curves that goes to this intersection point. And then from this intersection point to the next intersection point, I have another region, which I'm going to shade in a different color. If I want the area between these curves, I need to calculate the area of both of these. So when I look at the purple region, it's the cubic that's defining the top of the region. However, the blue region, you can see, has an upper boundary created by the parabola. And that's what we mean by switching the boundaries. These two different regions have different top and bottom functions. So we're going to treat them as separate integrals. So I'm going to write my first integral to go from the first intersection point at x equals -2 to the second one at x equals 0. My top function here is the cubic, so that should go first because we always do top minus bottom. And with this one, I'm going to want to be exceptionally careful because my bottom function is a binomial, and we're going to have to distribute that subtraction sign. So the bottom boundary of the purple region is created by the parabola -x squared plus 2x dx. And the very first thing I'm going to do is going to be to distribute that through. All right, I'm going to clean this up and then we'll look at the area of the second region. So after distributing, I got the second step here. And then when I combine like terms, I'm left with this as my integral to evaluate. And I'm going to leave it to you to verify that when you take the antiderivative and use fundamental theorem of calculus, you end up getting +12 for this integral. Again, I feel like by now you know how to integrate this well enough that I don't need to go step by step through that. So that's my first area. Now I need to calculate the area of region 2. For region 2, my limits of integration go from a left intersection point of x equals 0 to the right intersection point of x equals 2. So this will be the integral from 0 to 2. My topmost function is now the parabola. So that's the -x squared plus 2x minus the bottom boundary is formed by the cubic. And again, make sure you keep this in parentheses because this has multiple terms. We're going to need to distribute the subtraction sign through. All right, after distributing and combining like terms, I'm now left to integrate -3x cubed plus 12x dx, very similar to my last one. And again, I'm going to leave it to you to go through the work of calculating that integral, but these are similar. We do get an area of 12 again. So the overall area between these two curves is going to be formed by adding up those two individual areas, and we're going to get a total of 24. Sometimes our functions might be written in terms of y, and in that case, it's most convenient to do your integration with respect to y. So instead of subtracting the upper function minus the lower, in that situation, you want to think about it as the right boundary minus the left boundary. So take a look at this next example. It says find the area of the region bounded by the graphs of x equals 3 minus y squared and y equals x minus 1. So first I want to identify that area between these two functions, which would be this blue area right here. You have one equation here that's in terms of y, and the other one's in terms of x. And we need to get those to agree. So either both need to be in terms of y or both in terms of x. And the way you kind of decide that is look at where your intersection values are. If I look for my intersection points, I have an x equals -1 intersection point, and I have an intersection point at x equals 2. Now, the only trouble here is my area expands beyond one of those intersection points. And when you use limits of integration, you must use the points of intersection. So I run into a problem here. If instead you kind of turn your head sideways and look at the y coordinates of your intersection points, this one has a y value of -2. This one has a y value of +1, and my entire shaded region stays between these two values. So I want my limits of integration to be from -2 to 1, and I want them to be y values. But as soon as I want to integrate in terms of y, I will no longer be integrating top to bottom. I'm going to do right boundary minus left boundary. So I start to substitute those boundaries. Now, when you're establishing right boundary and left boundary, even though we kind of turn our heads to the side to look for the intersection points, when you're reading right boundary, left boundary, make sure you're just looking at the graph straight on. So the right edge of this shaded region is being bound by the parabola, which is this one, x equals 3 minus y squared. So that's perfect. Minus, now for my left boundary, that's the line. I don't want to use the equation of the line as it's written here because it introduces a second variable. I need this integral to be entirely in terms of y. So this is not going to work. What I need to do instead is I take my original equation, which is solve for y, and just solve it for x by adding 1 on both sides. So I'll get y plus 1 is x. Now, both of my equations are written in terms of x, so when I substitute, I get an integral in terms of y. All that's left now is to go through and integrate, use fundamental theorem of calculus. So I'll encourage you to pause the video here and resume watching once you've had a chance to do this by hand. Check your work against mine, and the correct answer for this problem is 4.5. There's one last topic to cover in this section, and that's arc length. Again, this is another kind of measurement. Sometimes we measure areas, sometimes we actually just want to measure the length of a curve between 2 points. And we can do that by integrating. And here's why. Let's begin with example 6 and thinking about how long is the curve y equals sine x from x equals 0 to x equals pi. And it says first try to estimate the length. I'm going to begin by just making a table of values and getting a graph to look at. And I'm going to choose 0, pi over 4, pi over 2, 3 pi over 4, and pi. And what this will do is it's going to break up my curve into 4 segments to begin with. So sine of 0 is 0. Sine of pi over 4 is radical 2 over 2. Sine of pi over 2 is 1. Then square root of 2 over 2. And then at pi, you're back at 0. All right, not my best work, but there you have it. So what we're being asked is to estimate the length. Traditionally, we measure lengths that are straight. So instead of thinking of this graph as a curve, I can think about it as this segment between the first 2 points, then this segment between the next two, and then this segment, and finally this segment. So straight line distances I am able to find. The tool that we use for that is the distance formula. It may have been a while since you've seen distance formula. First, you need to know the formula, which is you always subtract the x coordinates of the 2 points you're finding the length between, and then add the difference in the y coordinates. And this is derived from Pythagorean theorem. You may have learned how to do this using Pythagorean theorem. But the idea is I can find the length of this first segment, which goes from the point 0, 0 to pi over 4 radical 2 over 2 by substituting into this formula. I'm going to choose for my x2 to be pi over 4 and my x1 to be 0. So I have pi over 4 minus 0 squared. My y2 is then square root of 2 over 2, and my y1 is 0. So I have square root of 2 over 2 minus 0 squared. Obviously, subtracting 0 doesn't do anything, so I'm really left to square pi over 4. So that's going to be pi squared over 16. And I'm going to square this square root of 2 over 2, which is going to becomes 2 over 4, which reduces to 1/2. And that's still under the square root sign. So this will be that first distance. And if you calculate that on a calculator, you're going to get approximately 0.342. And that's the straight line distance, which again will just be an estimate of the actual distance along the curve, but it's probably a decent one. Now, it is tedious because I would now need to find the length of segment 2, the length of segment 3, the length of red segment 4, and I need to add those up to get the total distance from 0 to pi along this curve. And your textbook does go ahead and do this work for you. So it turns out it's approximately 3.7901. You've seen how when we were approximating areas, the more subintervals we used, the better the approximation got. And the same is true here. If instead of breaking my interval up into 4 subintervals, I were to do 20 or 50 or 100, I would get an even better approximation. And in fact, in your textbook, they do calculate with 100 segments what you get to be the total distance, and it ends up being 3.8201. Well, the good news is that you can see how there's this idea of a limit built in, where the more subintervals that we use, the more the approximation is going to converge to the actual value. And there is a formula which is derived in your book, so you can look there if you want to see where it comes from, that says when you want to calculate the arc length, the length along a curve, you can do it by integrating. Notice this is the first derivative of the function squared plus 1. Take the square root of all of that. And that'll give you the length from point A to point B. So if we were to apply that to this example, my function in this example was sine of x. Therefore, my derivative would be cosine of x. And so if I substitute into the arc length formula, it says I would form the integral from, in this case, we're going from 0 to pi of the square root of the first derivative, which is cosine of x, squared plus 1 dx. The resulting integral may be one that you're able to compute by hand. It may also turn out that there's no convenient method for integrating it. And what I need you to remember is the very first thing we learned was to use approximating sums to find the values of integrals. And this is actually a case where that's the best thing you can do, is find the midpoint sum. And again, your book does 100 subintervals. So you would use a calculator like the Riemann sum calculator that we used before. And you'll find out that the length turns out to be 3.8202, which is pretty close to the distance formula approximation. Instead of using the Riemann sum calculator for your homework, I'm going to give you two problems to do where I'd like you to use Mathematica for your integral evaluation. And then the last one I do want you to do by hand. If you take this particular function and integrate it in Mathematica from 0 to pi, you get 3.8202, which is the same as the midpoint approximation for this integral. So finding the length of curves is not super difficult, provided you can find the first derivative. And then, like I said, the integration, if it's too difficult, you would use some form of an approximation, or you'd use software. Or if you can integrate it by hand, you would go ahead and do that.